All right, so that's what I needed, to lose 3 minutes. I already reduced the length of this. So yeah, today I want to talk about following the water throughout our solar system. What's special? All right, so wanted to start with Venus, life in the clouds. So one of my favorite things about Venus is it kind of conjures those castles in the clouds, these different architectures that we don't think of. And in talking to some of my colleagues, there's, as you know, there's a couple different ways that water could have come to Earth. And we're always looking at the D to H ratio of asteroids and comets, trying to figure out what's going to match Earth. We look at the ice giants, we look at our gas giants, and we try to figure out how much, what the ratios were of the accretion disks early on in the solar system. And then we try to figure out how much is lost over time. I've been talking to a bunch of geologists who have been telling me that the water actually on Earth likely comes, like we're finding more and more on Mars, from subsurface. So every volcanic eruption, we actually get huge water deposits into our atmosphere from Earth. So within this, we started looking at if there is water that is continually being spewed into the atmosphere of Venus, if once upon a time it was habitable, which we may likely find out is true, could there still be extremophiles in the atmosphere of Venus? So started working, because we've seen, phosphine, we've seen some things debated, I know, but to me this is exciting. The more debate there is, the more we need to go, the more I need to make a very accurate spacecraft or robotic mission to be able to answer some of these questions. But in looking at the atmosphere, we came up with a couple of good ideas, and this is just going to the phosphine debate. This is all from Jim Cutts, who has been a really fantastic supporter and collaborator in all of this. So some of the work that I've worked with him on is looking at long-duration solar airplanes, the high-altitude balloon. We're doing the variable altitude balloon. But one of the things that really is fun within this is both looking at how we could get surface samples, specifically from the highlands that hopefully haven't been resurfaced, to see if there once was oceans or if there's anything that could be hydrated. The other one is I worked on a tow body which could be towed behind one of these craft, and then we could go deep down into the sulfuric acid clouds, be pulled back up through it, and look for a hydropause to see if we do actually have water condensate that we could sample and see if there is any potential life. And then I wanted to give a shout out to everyone here, because I'm deeply impressed with all of the work that's being done on where the origins of life could be coming from. I read this paper actually as I was putting this together, and the droplet world I find fascinating. A lot of the work I've been doing with Lori Barge is specifically looking at hydrothermal vents, and if anyone has suggestions on how we actually determine if this is the mechanism or a mechanism for life in our solar system and a good place to go, please share it with me. But the next place I wanted to go is the moon, because it's the one place in the solar system outside of Earth I know that we can find life. I have had many people tell me that there's reasons why we can't, but the reason why I'm sure you can find life on the moon is because we've left it there. There are piles of refuse from Apollo that we could definitely go and we could test some of our different sampling systems, some of our different life detection instruments, and we could determine, are they actually up to the task of going beyond the moon? So problem is I'm being told people want to turn it into a World Heritage Site. I think we could save a refuge pile for science. But to the moon, this is coming from my current work. So one of my current projects is actually Lunar Chopper. You're the first people to ever see it outside of JPL, basically with the re-architecting that's going on from the Mars sample return. This is something that we've really been pushing, is basically taking a lot of the electronics, a lot of the things that we've been utilizing on Mars, and repurposing it. So for Mars, I wanted to break it into two different places to look for life. So of course, the obvious one is the surface, the ongoing MSR. So in the beginning, when we were getting these samples, I'm reading about it, I'm like, cool, hydrated igneous rocks. Me, an individual, I don't really care so much. But then as we started finding sedimentary rocks, and specifically I think it's the magic one, lead scientist is like, oh yeah, if that was Earth, we would definitely have fossilized single-cell organisms. So it got me really excited to want to help bring some of these samples back. I actually had gone to Blue Origin. I left Blue Origin specifically to come back to JPL to work on this awesome new task of the sample recovery helicopters. So as the gripper lead for the sample recovery helicopters, specifically trying to bring these samples back from Mars. So we got to do some really cool, really lightweight technology development that gave me the ability to do a lot of materials and manufacturing, kind of pushing the limit to be able to achieve it. And now you're the first people to ever see the culmination of that. So we actually put this together, built the whole thing. This thing flies, so we flew it around as well. So we had this robot that could fly, drive, and then you can see my gripper there. The reason why there's two is we actually use it to be able to determine when we're in contact by braille. It also gives us this ability to drop any of the rocks that we were picking up. So we couldn't find something fully robust to rocks. I even built a rake at some point. My kids loved that I built a space rake. They joke that I rake dirt at work, and they're not wrong. But in putting all of this together, we came up with a really robust solution that was also autonomous. And that demonstration was the day before our first set of layoffs. But another fun thing that I got to do is I was the hardware delivery lead for the test bed sample transfer arm. I know it's being built in Europe, so we took this video actually just before I came out here, where you can see kind of what the end-to-end was meant to be, where we picked the sample tube up, and we drop it off, and then we're able to pick it up with the sample transfer arm, and then put it into the OS, the orbiting sample holder. And both of these were really fun robotic systems to work on, and being able to see them work in collaboration is something that actually feels really good. And I think my friends put this together to make me feel better about everything. They're like, well, your stuff works. So depending on re-architectures, we'll get to see how much of this we use, but these technologies are all very robust at this point, and we're hoping to find some really fun use cases in the near term. All right, I'm going to move forward through this because we've got lots of other places. You know how it then comes back, and I'll share all of this with everyone. I got this through our universal release system, so it can be shared. So where are we going now? So we've focused all of our energies from this group of people who's been working helicopters for a long time, and network issue. We now have over 2-meter diameter helicopter that we're looking to really do these next Mars science exploration missions with. The cool thing about that is you can have much more payload. We can access all over the solar system, and then we can also get into some of the underground areas. So this is the segue to the Mars underground. So thank you for Mars being hit by an asteroid. We now know that there is a lot of water on Mars. We don't know if it's in clays. We don't know if it's in hydrates. I did work a project where we were launching out a big sounder to be able to look for aquifers. But if there was life on Mars, which there's a good chance there was, but that's a conversation for later. I'm not saying it started there, but there's, yeah, I guess I'll have to follow up with that. NASA came out and said we're allowed to bring the samples back from Mars because since the point that there would have been life on Mars and there was life on Earth, we've exchanged so much that if there was anything that would wipe life out here, it already would have gotten here. And I was like, that is a really weird way to confirm panspermia without any fanfare whatsoever. How does the scientific community feel about that? But the official reason to allow us to bring the samples back into our atmosphere, which includes the moon, is essentially the statement that we're sharing so much from the heavy bombardments that we should be fine. I thought that was huge statement. But to that, we're currently working a deep drill. So this is one of my good friends, Felipe Tosi, where we're looking to be able to get down 10 to 100 meters, where you start getting to the point where we can find, if not extant, hibernating life, if it was there. So some of these next generation technologies are actually coming a long way. This is another one where this is one of the first times we're able to get it out. And this picture, the bottom right, was done by one of my good friends as one of his last works before he's moved on to other things. Now I want to move out to what more people are aware of when it comes to ocean worlds. And within that we have Europa, right, which is the obvious one, which we have the Europa Clipper going to. One of my favorite things to work on for Europa was a couple. One was the landing systems, also mobility systems when it gets to the chaos terrain. And we have a proposal in right now to come up with a embodied intelligent landing system for all of these bodies throughout our solar system. Something that allows landers to land repeatedly wherever they go, which is definitely, at least in the news, been a challenge for many people. So to this, I worked on Cryosimian, and so Cryosimian is a version of RoboSimian, where we worked through all these different mobilities, did the wheels, the spring wheels. I was actually working with the Fetch rover on that as a surface access technology, but then I also worked a lot on melt probes. So built a couple melt probes. I've got a good friend, Ben Hockman, who very much is a proponent of this, and he has one that's going to one of the ice fields later on this year, where they're trying to get down to lake and look at some of the extremophiles that are there. So this has been a really fun technology, but as you know, it takes probably another decade once we land on the surface of Europa to be able to get through the ice shell. And as we start getting through the ice shell, we actually get the ability to look at a planetary crust in a way that we probably can't ever do on another body. And because of the pressures, this actually is going to behave very much like a crust. So as we go through, we get a full transect. So I know a bunch of geologists that are really, really interested in everything we can learn as we move through. And this is one that's active, right? It's almost a form of tectonics with the more buoyant warm ice pushing up against the cold ice and leading to the mixing. That means all of the chemicals on the surface coming from Io are getting down into the subsurface. And with the 3 redox gradients coming probably from, hydrothermal vents, then from the radiation, and from the crazy pressure swings in such a thick ice shell, there's a lot of things that could have actually driven life. So now I really like this technology to get down to the ocean. There's a bunch of ways you can kind of drive it, get it to curve around things, sense them, get the information back. But one of the things I'm currently working is what do you do once you get there? So this is a little video from one of my friends, Ethan Scaler, who did swim. And so we have a bunch of little robots we're looking. And these we're looking to do chemical gradient following to actually look for hydrothermal vents here on Earth. And so another variant of this that is currently funded by the ONR, where I'm working with Brown University. Professor Monica there is leading this, but we're making swarms of tiny little shrimp. And these little shrimp are another thing that we can actually use to be able to look for life, on another body, but here on Earth as well, we can monitor the water columns throughout the ocean. And we can start understanding algae blooms, and we can start understanding all sorts of different biotransport. So now I want to take you to Titan. Titan was one of my favorites when I first started for obvious reasons. Cassini had the Huygens probe that landed on it. Cassini has been a huge, huge inspiration to me. It was the big mission when I first started my career. And so within Titan, let's see, right? We know we have this great atmosphere. We know that if you had styrofoam wings, you could fly. We know that if you put a park on, the pressure allows your blood not to boil. There's a lot of reasons why Titan may be a variant of what an early Earth looked like, right? We know it also has a liquid ocean underneath. So this is just a really, really fascinating body in our solar system. And I also learned it's leaving Saturn's gravity well. So interesting stuff there if you want to go out far enough. So in the early days, in looking at all of this, I was looking at access technologies. So we had a variant of the balloon missions we've kind of repurposed to Venus, but within, putting all of these maps together, realize that this is the only other body in the solar system that has active alluvial created caves. And so these caves are something that I would really like to get a robot into. To that, for some reason, I wasn't able to connect to internet, but this is all online. I'm a co-I on this great shapeshifter idea where we had a bunch of drones that can actually turn into little submarines and turn into a ball to be able to get more endurance because they actually use a lot less power to be able to go further away from the balloon, and then they can be a heavy lift device to bring samples back to this proposed balloon mission we were working. At the time, it's also why we had Squid, which is a launched aerobraking drone that we were looking to also bring samples back to balloons on Titan. And that's something that you actually see in that heritage of both Lunar Chopper and some of these, future ideas that we're pushing. So I don't want to spend too much time here because I know I don't have a ton of time left, but this is such a cool mission. As much as I loved what I was working on, the selection of Dragonfly, while it's ended looking at alternate technologies, the knowledge that this is going to happen in our lifetimes, that this is ongoing, getting to see the work, talk to my colleagues who are building it. For a while I worked in the honeybee facility when I was at Blue Origin and got to see it actively come together. This is a very, very cool mission. Let's see, and I think the next one is also online, which no network. So let's move beyond Titan. And let's move to the one I'm probably best known for, Enceladus. So never negate the weird paths that life takes you. My initial, I was born in Colorado in the snow. I just spent 10 days up in Niseko snowboarding. I very much love snow and ice and kind of the cryosphere of our world. So coming from that background, I had gone into hybrid air-breathing rocket engines, specifically I was specifically looking at shockwave cancellation geometries because we didn't have a shuttle at the time. And so I did a whole lot of supersonic flow and supersonic calculations. And then I got into wall climbing robots. So I had this really weird background, and I was sitting there as Cassini was going through the flow on Enceladus, and I started doing a bunch of calculations coming from, the different data points that we were getting back. Right? So we had a good idea about the temperature. We know the mass flux quite well. Thank you for giving us all of the plume gases and why we're very interested specifically to go to Enceladus. And we all wish the mass spectrometer on Cassini could have gotten some of the heavier molecules because maybe it saw more than just a habitable ocean and some silica that gives us the idea that there's hydrothermal vents underneath. So there's a bunch of cool missions that we're working on to go back, but the one that I got really excited about as OWLS, the Ocean World Life Surveyor, was coming together. I was like, cool, so where do you want to take it? You want to take it to an ocean, and there's an open window. So in looking at it, we found that there was essentially, I'm an engineer. I don't need to know what's there. I need to know the bounds of what's there to make sure the mission can be successful. So there was two different ways two bounds, I'll call it, envelopes. There was the open crevasse, where it's just boiling. So this is the Kite and Rubin model. And then there was the Kalind-Porco model, where this is cryovolcanism. And then there's a bunch of different things where it could be, things coming out of solution, where you have your gases coming out of solution and it's, a soda bottle you shook up on the right-hand side. Or it could be something where in that expansion, it's actually causing more freezing underneath the ice, which is putting more pressure on it. But to me, all that really mattered is the geometries. So on one side, we can essentially fall as long as you can fall within, it's only going to be 1 kilometer by the hydrostatic pressure to be able to get down to the ocean. So you may be able to fall, but very quickly you start getting to a point where a tungsten ball won't fall. But a rod of a certain length would be able to fall down, except for if it gets into this other Kalind-Porco one, where you get to this converging diverging nozzle, which is your wind tunnel. So it was really fun to actually look at a wind tunnel and come up with a way that we might be able to climb through an active wind tunnel and look for what's underneath. So instead of showing you the stuff that you've seen from Hero, from me, from other people, I wanted to show you something where, unless you've been to a planetarium show, you haven't been able to see. This was a great collaboration where we had the South Pole, we have these vents, and the thing that's really driving our interest is the silica grains. The silica grains would have had to come from, interaction with the magma underneath. And that interaction with the magma would have made sure that we have a lot of dissolved minerals in the water. As that cooled, we'll probably be making hydrothermal vents. So with that fundamentals, it's like, oh, hydrothermal vents underneath the South Pole may be a fantastic place for life. And one of the things that I love about Enceladus is it's new, right? It's very new. There's a good chance it's a reaccretion from something that happened in the Saturnian rings. It's an overpressurized system that isn't getting intrusions of things from Io and other places within the solar system. So it becomes this pristine area to be able to start looking to see if some of these concepts, some of these theories, is how life arises and the speed that does. It also gives us the ability to understand a prebiotic ocean, which to me is fantastic because life has eaten all of the chemistry out of the bedrock of Earth. Oh, calculating the changes you would see in buoyancy. I learned a lot about buoyancy to help them with this. But then as these gases are coming up for Cassini to climb through, I loved how they added eels in here. So this was my idea for a falling robot that could also be able to get down through the vent, and it becomes a robot that can swim because at 100th gravity, each one of these screws is also a propeller. And you don't need much thrust at 100th gravity, even if you are very negatively buoyant, to stay at the water-ice interface. And the water-ice interface is where you would have any of your gases from hydrothermal vents that would stay there. So think of it as fish heads, something that would attract life to be able to kind of consume the excess energy in that system. And then as we move out, a great thing that this group did is they actually looked beyond the solar system. But one of the things I wanted to throw in here that I've been talking to Carl Mitchell about is it looks like Triton may actually have an ocean underneath. And you can see those dark spots. Those may actually be cryovolcanoes. So if those turn out to be cryovolcanoes, we may actually have another ocean world even further out, another fantastic place to design a access technology to be able to see. So in the last 5 minutes, let me go beyond our solar system. So we have the starshade, and so that's actually, I have a really good friend here, Sage Moray. We just did an installation using the Starshade, and the Starshade is a really cool next generation mission where we're looking to do occultation to be able to block out the light from a star, to be able to image the, to be able to magnify the light that is reflected off exoplanets to be able to image it directly. So in being able to do this, what we're actually looking for, you would need to do gravity lensing to be able to see a planet directly. But what we're able to do here is we can start looking for the fingerprints of life. So instead of the amino acids that we see in the background of, a nebula or throughout the universe, we can start looking for the shifting of the amino acid fingerprint like we see when we look at Earth. So we know what it is and how it gets shifted within our own world, but now we can start looking out and inferring what that could mean at exoplanets around stars throughout the solar system. Excellent. I'll let this play out, but that is it.